What's up everybody? Welcome back. Moving on with rate of change. We're now going to be doing an example that comes up fairly often in this unit. So water is being poured in these containers at a constant rate. Draw water level versus time graph for each of these. Okay, so a water level versus time graph. Now what do we mean by water level? Well, just basically the height of the water in the containers. And if you notice, because water is being poured into these containers, what's going to be happening with the water level for all of them? Well, the water level is going to be increasing, right? So that's the first thing we know. The water level is increasing for all of these containers. So we know all of these graphs are going to be increasing graphs because we're graphing the water level versus the time, and the water level is increasing as time goes on, as water is being poured. However, what's going to change is the rate of change of the water level. And that all depends on the diameter of the container. So, if the diameter of a container is constant, that means that the rate of change of increasing water level is constant as well. And that makes sense because if the diameter is not changing and we are just pouring water into a container, well, the water level is going up at a constant rate. So if the diameter is constant of a container at some point in the container, then the rate of change of increasing water level is constant as well. Now, what about a case where the diameter is decreasing? What does that mean? Well, this here is a good example. Notice how the diameter is very large at the bottom of the container, and then the diameter is decreasing as we move up the container. Well, if the diameter is decreasing rather, the rate of change of increasing water level is increasing. Why is that? Because if we're pouring water at a constant rate for a larger diameter container, it means that the water level is going to rise up more slowly because there's just more container to fill. It has a larger diameter. So the water level is going to rise up slowly at first, but as the diameter is decreasing, what's going to happen to that water level rate? Well, it's going to increase faster and faster and faster because there's less container to fill then. So whenever the diameter is decreasing of a container and you're filling in water, the water level, the rate of change of the water level is going to be increasing. And then the last scenario is what happens when the diameter is increasing. So a good example of that is maybe the top portion of this container. Or let's say we had like a container that looked like this, right? So notice how the diameter is smaller at the bottom than it is at the top. What's going to happen as we pour water in a container like that? Well, as the diameter is increasing, at first, when we're pouring water in, the water level is going to rise up fast, 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 but then it's going to slow down because then there is more container to fill up as we move up the container. So the rate of change is going to be decreasing. All right, so thought I would point these out before we start drawing these water level versus time graphs. I think it's important to realize this. Another thing I want to quickly mention is notice that this question is water being poured in, and water is always being poured in from the top. So obviously the water level is increasing. But you can also get questions where the water would be leaking, and it would be leaking from the bottom at a constant rate. And that would make the water level decrease. Okay, so it would be a different looking graph, the water level versus time graph. So just be aware of that. You can be asked both types of questions. In this case, we're being asked for water being poured in. So these would be the scenarios of water being poured in. But if water is leaking, then these may change. This is definitely going to change. The water level will be decreasing. So let's draw that first water level versus time graph for this container. So water is being poured in. Notice how this container has a constant diameter. So we know the water level is increasing and its rate of change is going to be constant. So it's just going to be a straight line like that, right? Water level is increasing. Diameter is constant, so it's increasing at a constant rate. So it's increasing at a constant rate, so it's just a straight line. If we draw a slope of a tangent on this line, all the slopes are going to be the same. Now, what about this container over here? So water level, I'll just label it as WL versus time. What's going to happen with this one? Well, notice how the diameter is constant for this one as well, but it's a much larger diameter than this container. So the water level is still increasing. It's still increasing at a constant rate, so it's still going to be a line, but it's going to be increasing a lot slower. So basically, this graph may look like that. Notice how it's a less steep line than this one. Both of them are increasing their water levels at a constant rate, so they're both lines that are positively sloped, but this one is filling up a lot faster than this one because this one has more diameter to fill. So the rate of change of this one is constant as well, but it's going to be a smaller rate of change than this graph here. Okay, now what about this container? So with this container, what's happening is the diameter is large at the bottom and then it's small at the top. So the diameter is decreasing. And what did we say? When the diameter is decreasing, it means the rate of change of the water level is increasing. That makes sense. When we're pouring water into this, water level at first is rising slowly because it has a lot of container to fill at the bottom. So it's rising slowly, 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 and then it starts rising faster and faster. So water level is always rising, but it's rising slow at first, and then it gets quicker and quicker. Right? So water level's rising, and the rate of change, if we draw some slopes of the tangents, it is increasing. The slopes of the tangents are getting more and more steep. So water level's rising at an increasing rate. Okay, now what about this container? Now this container is a little bit more tough because it has multiple parts to it. Okay, so notice how from here to about here, the diameter is what? It is maybe even down here. From here all the way to there, the diameter is what? It's increasing. And then the diameter is decreasing up until this point, and then it starts increasing again. All right, so let's make a note of that. So from here to here, right, the diameter is increasing. This is the diameter, representing it by the arrow. So the diameter is increasing. Then from here to here, the diameter is decreasing. And then from here to there, the diameter is increasing again. So it's not constant at all. The water level is always rising, but the rate of changes are going to be different. Okay, so let's start off with this first phase here, filling this container. the diameter is increasing, meaning that when we're pouring water in, at first the water level is going to rise fast because there's less container to fill at the bottom, but the diameter is increasing, so the water level is going to rise more slowly. So the first part of the graph is going to look something like that. Right? So water level is rising, but at a decreasing rate of change. If we draw slopes of the tangents, the slopes are going to get less steep. Then what happens is we reach this point, water is still being poured in at a constant rate, but now the diameter is decreasing. And when the diameter is decreasing, what's happening? Well, we already shown in this graph that the water level goes up at an increasing rate of change. So for that phase, it's going to look something like that. Right? So it goes up at a decreasing rate of change, and then the rate of change is going to increase. If we start drawing slopes of tangents for this portion of the graph, the slopes will start getting steeper and steeper. And then, let's say at this point in time, so somewhere over here, we reach this portion of the container, water still being poured in, but now the diameter is increasing again, meaning that the water level is going to rise up slower and slower and slower. So the water level is still going to rise up, but it's going to be slower and slower, so it's going to look something like that. All right, so notice how this graph, it has 3 different parts to it because the diameter was changing in 3 different ways for this container. And in these 3 containers, the water level was changing the same way. Or the diameter was changing the same way. It was constant here, and then the diameter was decreasing here. Well, here, diameter is increasing, then decreasing, then increasing. So we have to have 3 different parts to our graph. So water level is always increasing, but first the rate of change is decreasing, then it's increasing, then it is decreasing again. So that's pretty much it. So what you want to look for, you'll probably, if you do get a question on the test, I'm guessing you'll be more like this. So all you do then is just split up the container into different parts and see what's happening with the diameters. And then, however many parts you split the container up into, you split your graph up into that many parts as well. And then just use those scenarios that we wrote down before. What's happening when the diameter is constant or when it's increasing, decreasing, etc. Yo, what's up guys? Thanks for checking out my channel. Hopefully you got some value from the video you just watched. If you did get some value, big favor to ask you, please like this video and subscribe to the channel. Any questions, any recommendations on things you'd like to see, please leave it in the comments section. Also check out the description box below for links to material and content related to the video you just watched. Peace out.